buenos días a todos. Mi nombre es Rodrigo Vázquez, asesor senior del programa Energía 4E de la GIZ y encargado de hidrógeno en el proyecto de descarbonización del sector de energía en Chile. Pero antes de hablar de las charlas técnicas, queríamos, por parte de la GIZ, desear que todos ustedes y sus familias se encuentren bien y esperamos pronto volver a conocerlos en persona, así que vamos que se puede. Bueno, nuevamente darles la bienvenida a esta nueva e interesante charla técnica. Ya es la tercera en el ciclo de charlas que GIZ está organizando junto con el Ministerio de Energía. Y estas charlas además son patrocinadas por la Asociación Chilena de Hidrógeno, H2 Chile, el Centro UC de Energía, la Universidad Técnica Federico Santa María, el Comité Solar e Innovación Energética de Corfo y la revista Electricidad. Antes de presentar al expositor de hoy, les comento que en los próximos días le llegará una invitación para la siguiente charla técnica del 6 de agosto, donde la empresa Bosch presentará la tecnología de calderas que utilizan hasta 100% de hidrógeno. Así que eso es consideramos que es un gran paso para la sustentabilidad del calor industrial, así que no se la pierdan. Bueno, ahora lo que venimos. Como introducción, actualmente varios países europeos están realizando estudios sobre la inyección de hidrógeno en las redes de gas, así como la metanación con H2. En junio pasado, los operadores de redes de gas franceses publican el informe Condiciones técnicas y económicas para inyectar hidrógeno en las redes de gas natural. Posteriormente, el 17 de julio, la semana pasada, 11 operadores de gas europeos de nuevos Estados miembros presentan el plan European Hydrogen Backbone para una infraestructura de transporte de hidrógeno dedicada. El gobierno británico publicó ayer, 22 de julio, su compromiso de 350 millones de libras esterlinas para la recuperación verde, y de los cuales 139 millones serán destinadas para reducir las emisiones en la industria pesada, al apoyar la transición del gas natural a la energía limpia del hidrógeno. La cantidad de energía que se puede transportar por las redes de gas es inmensa, con pérdidas marginales, estamos hablando del 0,7%, o sea, 0,7%, lo que representa una gran oportunidad de llegar con hidrógeno a grandes y pequeños consumidores, o sea, desde empresas hasta sectores residenciales. Entonces, en este escenario vemos la importancia que tiene conocer el estado de arte de la tecnología Power to Gas, y para esto quería presentarle a nuestro expositor Jachin Gorre. Jachin es ingeniero de energía y medio ambiente y tiene un posgrado en ingeniería de proceso, con un enfoque en ingeniería de procesos químicos y energéticos. Después de su paso por la Universidad HSR, la Hochschule für Technik Rapperswil, este año finalmente funda la empresa Grinix y utiliza toda su experiencia en la gestión de proyectos, conceptualización y diseño de plantas para estudio de viabilidad, evaluación técnico-económica de proyectos Power to Gas, acoplamiento de los sectores calor, electricidad y movilidad, el denominado sector coupling. Jachin entonces nos presentará Power to Gas in Europe, Project STORE&GO. La presentación será en inglés y nosotros iremos recopilando las preguntas del chat. No es necesario que la haga en inglés, ¿ya? Nosotros la vamos a ir traduciendo al expositor, para que al final de la presentación Jachin pueda contestarla. Ahora voy a cambiar de idioma para invitar a Jachin. Ok, Jachin, it's your turn. Please activate your microphone and screen of your. Please go ahead.
Okay. Thank you for sharing the opportunity, or give me the opportunity to present here the project STORE&GO. Dear ladies and gentlemen, also from my side, a warm welcome to my presentation. My name is Jachin Gorre and I am the founder and managing director of Grinix. And as you already heard, in my professional career so far, I've been intensively involved with power to gas, from preliminary study and feasibility analysis up to the construction, commissioning and operation of power to gas plants. Grinix is an independent consulting company for technical and conceptual development and implementation of profitable solutions for production and use of renewable gases. Through the combination of our expertise, dynamics, ambition and pragmatism, Grinix finds future-oriented and profitable solutions for the energy turnaround for all its customers. So with this expertise, the founders of Grinix were able to make a special contribution to the STORE&GO project in Europe. And now I would like to present you the project and the results of it. So I start with the facts and figures. In the European Union, the project was funded and 27 European partners have investigated the potential of power-to-gas applications in the European energy grid as an important step for the energy transition. One research question was, how can Europe reduce its carbon footprint and at the same time cover large parts of its future energy demand by making the most efficient use of renewable energies, so wind, PV, biomass, for example, or water. The consortium sees in power-to-gas the most promising way to store large amounts of energy. So the scope of the project was to investigate several reactor types of power-to-gas processes and production concepts for methanation in the megawatt scale, so in the big scale. And also one scope was to determine effects of power-to-gas on the electricity grid and on the gas network, and to analyze technical, economically, and ecological and legal aspects, so techno-economic analysis and business case development. At the end of the project, all partners summarized the results of the project in a European power-to-gas roadmap, where some recommendations for power-to-gas applications and for the political persons are written. So in the perspective of a short, mid and long term, what should all the countries in Europe do to give power-to-gas a chance that power-to-gas is part of the energy turnaround? The project was structured in 9 work packages. So it was work package 5 to 8, the so-called cross-cutting activities with some theoretical studies. But behind that theoretical studies, there are 3 demo sites in Germany, 1 in Switzerland, also and in Italy. And all 3 demo sites give the theoretical studies some practical experience. And in work package 9, made sure that the results could be made available to the wide audience, like you now, also in Chile. So you can find all public results on the project homepage. I will show you later. In STORE&GO, we had 3 demo sites, as already mentioned. 1 in Germany, Switzerland, and Italy. All 3 locations have different focuses in the field of renewable energies. In northern Germany, there are many wind turbines. In Switzerland, here, there's more hydropower from the Alps. And in Italy, here, we have, especially in the south and near to the sea, we have a lot of PV, so photovoltaic, solar power, and wind. And in Switzerland, for example, biological methanation was used, while the other both demo sites used classical chemical reactor technology for the power-to-gas process to produce methane. The so-called cross-cutting activities are listed here, and they deal with, as mentioned, techno-economical and ecological evaluation of the technology and some seasonal influence of power-to-gas to the energy system or to the connected networks, gas network and electricity network. And also from macroeconomic and political barriers, we take a look also to the outlook on the demand for synthetic fuels in the near future. So where and when do we need green gases or green molecules? But what was the motivation? Why did the European Union put this research question in the call for proposals? So the long-term goal is to limit the rise in temperature and reduce CO2 emission. In the graph on the left-hand side, it's the expected CO2 reduction in Europe. You see here from 2005 to 2050, the expected CO2 reduction in million tons CO2 equivalent. And at the end, in 2050, the goal of the European Union is to be CO2 neutral. But to reach climate goals, we will need innovative technologies to unlock the potential of renewable energies in the whole world. And power to gas is one technology which will provide a tool to decarbonize the energy system by producing green gas, which can be stored for balancing the energy grid and for providing gas as a backup for power generation. If there's not enough wind or PV, for example, at night, then we can use some gas-fired power plants, but they are fed with green gas, not with fossil fuel. Or power to gas is also able to provide green fuel for cars or for transport systems, or heating, and also methane or some other green gases or liquids can be also used as feedstock for energy carrier for the industrial sector. So currently, up to 80% of the global energy consumption here, as shown at the right, is provided by molecules and not by electrons. So it's not possible to decarbonize the whole world with electrons. You will always have some molecules in your energy system. And power to gas can therefore be a useful instrument, not only for the electricity grid, but also to reduce dependence of fossil energy and raw material sources in other areas. For power to gas, the application that cannot be electrified and the technologies that require high carbon input material are also important. Even if there are more efficient technologies for example, grid services like batteries, power to gas can place the advantages of the molecule and in Europe of the existing infrastructure. For example, molecules can be distributed with the actual built distribution system by pipeline, for example. It's already there. Molecules can easily to store and have storage possibilities for different durations. So you can store molecules today and use it in half a year or 1 year later. And also you can store a higher volume and at higher energy density than with electrons. Molecules require more complex systems to provide renewable energy, but this is on a long-term negotiable. Because at the moment, the infrastructure for molecules is already fitting the current demand, and at the requirements for renewable growth, capacities will be freed. So you could potentially be, or the infrastructure could potentially be used for green molecules. From the call, the European Union wrote in the call text when they asked for participation, the high penetration rates of variable renewable energy resources entail the need for large-scale energy sources. And here in that graph, you see why power to gas is the correct or the right technology to have large-scale and long-term energy storages. The discharge time is here shown over the storage capacity. So power to gas, power to methane, and power to hydrogen can store a great number of gigawatt hours up to terawatt hours of energy, and over days to months or even over years. So power to gas or synthetic natural gas or hydrogen is a perfect seasonal storage if it's needed. So in the project of STORE&GO, the core technologies are, of course, electrolysis and methanation. but in the call text it was asked to focus on methanation. And so we keep here the focus on that part here, methanation, where CO2 is needed and hydrogen. But of course, also some other technologies are needed. And on some location, we had also a focus on the carbon capture technology and the liquefied natural gas technology. So we do not only take a look at the gaseous medium of methane, but also of the liquefaction. So the first demo site is Falkenhagen. It's located in Germany. The project partners there have developed and tested a special chemical methanation. The catalyst is applied to a honeycomb surface. You see here the honeycomb modules. The catalyst is at the surface of that honeycombs to better transport the heat of the outer to the outer edge of the pipe where the coolant flows, because the reaction of hydrogen and CO2 is an exothermal reaction. So there's additional heat produced, and with this structure, the heat could be better transferred to the outside here. Here you see the reactor zone with around 180 tubes, these small things. And here you see how one of the honeycombs is put inside one of these tubes. At the end, this is the whole reactor, and the red marked element here, this is the reaction zone. And the reactor is integrated in a full power-to-gas plant with an electrolyzer unit. CO2 is stored here in that tank. It's from outside and or delivered from the outside. And a flare, if something happens, then that the methane is not put out to the atmosphere, but burnt to CO2. Here you see some operational experience from Falkenhagen. In the first graph, you see the volume flow. In red is the hydrogen flow, and in blue you see the CO2 flow. The CO2 flow in cubic meters per hour from CO2 is always a quarter of the hydrogen flow. And in green, you see the Sng, the synthetic natural gas, which is injected into the grid. So among other things, very successful, we showed here long-term trails in Falkenhagen, and also the flexibility has been tested here. So especially normally the electrolyzer is very can work with fluctuating energy demand, but the methanation is not so fast like the electrolyzer. So we try to find out where is the limit of the methanation to follow the electrolyzer. So in the second graph, we see at the same time range. In green, the methane content. You see also here with a better view the methane content in green over the whole period. In green dotted, it's the methanation concentration after the first reactor stage. Then there's a second reactor stage to increase the methane content. And in red, you see the hydrogen content after the first methanation stage, and in red also after the second methanation step. So the goal was to reach over 95% of methane in the product gas. So over the whole period of that operation period, you see that we reach always over 95% of methane. So we were always able to inject the gas and reach the necessary gas quality to inject to the grid. Here at point 2, you see some load changes from 67 up to 95% and vice versa without loss of quality. Here we change the load And here you see the methane quality after the second methanation reactor step, also here, and the quality stays nearly the same. So what have we seen here then? That the methanation technology is able also to run very flexible and very constant, undependent on the load. The second demo site in Switzerland is a biological methanation. It has been tested very successfully. Biological methanation has the advantage that it works at moderate temperatures at about 40 to 65 degrees Celsius. Chemical methanation normally works at 210 to 300 degrees Celsius. Here we used archaeas or bacteria. They convert carbon dioxide and hydrogen into methane and water. Depending on the process environment, so pH value, nutrients content, the stoichiometry of H2 and CO2, etc., they produce on a biological way methane and in a very high conversion rate. And here the gas was after one methanation reactor stage already so good, or the methanation concentration was so high that it could be directly feed into the gas grid. On the right hand side you see a sketch of the whole plant, of the whole methanation plant. Here's the methanation reactor, the tower. There's a liquid inside with these arches, an agitator to steer the media. Here is the feeding station, a liquid skid cord where the nutrients given to the arches, that they have something to eat. Next, beside the hydrogen and the CO2, they need some salt and the correct pH value. This is provided by these nutrient feeders. Also the chiller to cool down the gas and to condensate the water is positioned here. Then we have a technical area to heat and cool the methanation reactor depending on the outside temperature. Then we have the liquid skid here, the gas skid, sorry, there's a mistake. It's a gas skid where we purify the gas, so condensation of water also, and a drying unit to decrease the dew point to reach the necessary values for injecting the gas, and also a flare if the gas could not inject to the gas grid. You see a view from that side here to the plant. And that's on the top left, you see the methanation plant positioned here, and that's the electrolyzer unit and some other stuff which was already built up before we add the methanation unit. And also in Solothurn, the biological methanation is very flexible, even more flexible than the chemical methanation, because you have the volume of liquid inside the reactor which buffer a little bit the gases you put in. So here again you see in red some changes in the hydrogen flow from around 55 cubic meters up to 90 cubic meters per hour and vice versa. Then we stop immediately the plant. After a while we start up again from 0 to up to 80% and keep the load constant, decrease it, keep the load constant, increase, and so on. And also here you see then in green the injected gas. Nearly always we reach the quality to be able to inject. And here again, as you see here in the down, then green, the quality after the methanation reactor. We have two measurement points. They measure a little bit different, but let's say that the middle value of these two is the correct one. But we always, also in Switzerland, we always have to be higher than 95% of methane in the product gas. So we were always able to inject the methane to the grid. And in Troja, the last demo site, the Italian site, was something very special. There, most of the new technologies were operated together. The CO2 was, for example, extracted from the air with direct air capture. The methanation used a new reactor concept, and the product was subsequently liquefied. The millistructured and catalytic reactors are a new breakthrough technology compared to the conventional methanation technologies. They use small channels in the reactor, and the small channels allow a very high heat and mass transfer, so that the reaction is thermally well controlled. Here you see the methanation reactor, where the cooling media is coming in from that side, and from the top here the gas is going through the whole reactor, where the catalyst is inside in that small channel. Here again another sketch from the methanation reactor, and here without insulation you see the whole methanation reactor. The advantages of the millistructured reactor, as mentioned, is a high thermal control, so the temperature will not increase up to a temperature where the catalyst has an advanced aging, and it's a modular concept. Here you see 4 of these units. So if you want to increase the size of the methanation reactor, it's due to the modular concept very easy. And also if you have to do maintenance, you can exchange one of this unit. It's very compact and safe. Also here in Italy, we did some experiments with load fluctuation, and in the Italian demonstration plant, the chemical catalytic technology is used as mentioned here. We also did some load change, and the quality varies a little bit. Here you see the load change in red, and in green here the quality changed a little bit. But here the quality is after the first methanation stage a little bit lower, but then if you decrease the load, also the quality increases. But it's no problem, because after the first methanation stage there is always a gas upgrading unit, for example membranes, and then after the membrane, also in Italy, we reached the quality which is needed to inject to the grid. But in Italy, of course, we did not inject the gas in the grid, but we liquefied it, and therefore the methane content must be very high and pure, and very pure. So the membranes after the methanation reactor, they did a good job that there's no CO2, carbon dioxide, in the gas, so that the methane was able to be liquefied. And also here at point 2, for example, you see the flexibility that we can decrease the operation load up to 20%. Overall, from a technology perspective, the key messages from the project are that the power-to-gas technology at the STORE&GO demo sites are at high level of technology readiness, and we could show a complete range of technologies, and the combination, as mentioned for the demo site in Troja, we combine direct air capture with methanation, electrolyzer, and liquefaction. So a complete range of technologies are available, and if you are interested in the field of power-to-gas, you are able at the moment to choose the best suitable technology configuration for your specific power-to-gas plant. So small scale, large scale, or if you have alternating or continuous production or electricity supply, you can choose the technology which fits best. So power-to-gas is innovative and ready to use from our point of view. But there are some regulatory frameworks in Europe and market distortion currently, which are sometimes not bringing power to gas to the market at the moment because there's no feasible business case. But I will come to the problem within the next slides. One problem at the moment, let's say, are the costs. But I would like to show you an example from the PV system. Here you see the cost reduction over the last years or over the cumulative production. And also for the PV, you see each time the cumulative production doubled, the price went down by 24% for the last around 40 years. So cost reduction due to learning curve effects occurs to all industrial manufactured products, so also for power to gas. So we take a look at the cost reduction potential for power to gas. The learning rates of the components in the power to gas plant based on a literature study, but also on the data we got from the supplier of the demo site. So here you see from 2015 up to 2050, the yearly electrolysis production worldwide, the cumulative electrolysis production over the time. And we take 3 examples, a low, a moderate, and a high production of electricity of electrolysis up to 2050. This is a basic for our learning rates. So both main components of the power to gas technology, the electrolyzer and methanation system, display promising cost reduction results related to technological learning. So cost reduction through an increase of the production volume, but also in scaling effects. So cost reduction in consequences of an increase in size and form of upscaling. So here you see for the electrolyzer unit, for a high temperature electrolyzer, solid oxide electrolyzer, if you increase the size from 5 megawatt to 100 megawatt, here you see also a decrease in cost, in the specific cost in euro per kilowatt. So the produced volume of power to gas plants and therefore the chain experience will depend on the development of the future global demand for power to gas products, which is a subject to climate and policy issues, for example, carbon taxes, the scope of government R&D, subsidies and market introduction programs, and economy factors, for example, economic growth. So, of course, this is an outlook. It could happen that the costs in 2050 will not be there where we think at the end of our project. So, also for the power to gas units or the electrolyzer units, here we have an average learning rate of about 13% each time. So the production is doubled. The investment cost went down by 13%. That's the calculation we see for power to gas technology. And the high temperature electrolyzer the cost will decrease faster than the technology of alkaline electrolyzer and PEM electrolyzer, because they have a higher learning rate at the beginning because the technology is very new. The alkaline electrolyzer technology, the yellow one, is established since many years in the world, so the learning rates in future will not be too great, too big. Also for the methanation unit, we take a look at catalytic and biological methanation. The biological methanation, the blue one, is a newer technology, so the learning rates here are a little bit deeper. than the catalytic methanation, which is already more than 100 years old. And also here, over the whole system, if we take a look at the whole system, so heat exchanger, reactor technology, catalyst, and piping, and so on. If we combine all these learning rates of these units, the average learning rate of the whole power to methane system here is around 12%. In addition to the cost of the main subsystem, electrolysis and methanation, there are further costs to build a turnkey plant. These can be estimated in a first project phase with some add-on factors. In order to obtain a turnkey plant, the following aspects must be considered. So piping, instrumentation, and automation, building or a container, depending on how big the size will be. Site development, engineering, and construction of the plant, all items then represent the overall investment cost. Finally, the production costs for synthetic natural gas are composed of several components. So in addition to the depreciation of the investment cost, there are operating costs, as well as costs for electricity, water, and carbon dioxide. And ideally, the byproducts, oxygen and heat, can be also sold. So we take a look at the final production cost, depending on the combination where the electricity is coming from. So here we combine power to gas with a PV plant and a power to gas plant with wind. So the electricity is direct produced from a wind farm or a photovoltaic plant and is used directly in the methanation and the electrolyzer unit. It's not injected to the grid. So in early applications, like let's say today in 2020, the Sng production costs are relatively high since a large share of investment cost in blue, as you see here, makes the main piece of the cake. Let's say the main piece of the investment cost is due to the large share of investment here. The Sng production cost will increase if only surplus electricity is used, because a decrease of full load hours leads to a further increase of the share of investment cost. But if we go to the future, the cost reduction, as we've seen before, will decrease, and so we will come in a range in 2050 where the costs of synthetic natural gas are lower or even the same like fossil fuel. And the same is for wind, because you have higher full load hours if you connect a power to gas plant with a wind farm. You will have lower costs in 2020 and also a decrease of cost up to 2050. If we take a look at the Sng production cost for the scenario that the power to gas plant is directly connected to the grid, we have here in blue again the year 2020, in orange the year 2030, and in green 2050. And in the next years, there will be more and more renewable energy in the grid, so from wind power and from solar power. So there will be some hours in the year where we have too much energy in the grid. So the electricity has to be converted in or stored, or the wind farm has to stop producing electricity. So in the near future, in 2030, 2050, there will be a lot of hours where the electricity is very cheap or even negative price. So if we run the plant in 2050 over 2,000 to 3,000 hours per year, we will get the cheapest electricity price and therefore the best price of Sng, or the production cost of Sng, the best time is to operate only the power-to-gas plant in between 2,000 and 3,000 hours of operation. If we will operate the plant longer, then we have to pay higher electricity prices, and so the average Sng production cost will decrease. Up to now, today, it's the opposite, because at the moment we have not so much renewable energy which has to be stored. So we will have the lowest Sng production cost if we run the plant around 8,760 hours per year, so over the whole time. This will change in future, and then we will have two effects. We have low Sng production cost, and power to gas can be helpful to balance the grid, to give the electricity grid an incentive, and the renewable gas then can be converted again into electricity if there's no production of green electricity because it's at night or the wind is not blowing. Here again, the overview of the cost. Today in 2020, we have, if we connect a power to gas plant with a PV field, you have very, very high production costs for synthetic natural gas. The best case is to get electricity from the grid and operate the power to gas plant with 6,000 hours per year. In 2030, the best case is still to operate the plant with a grid, or connect the power to gas plant to the grid, but you only need 4,000 hours per year to reach around the same Sng production cost as in 2020. And in 2050, all three potential connections, PV and power to gas, wind and power to gas, and grid and power to gas, will have nearly the same gas production cost and around 10 euro cents per kilowatt hour. And here you see for the grid, you only need to operate the plant at around 3,000 hours per year. So the future there will be a change in operation modes for the future for a power to gas plant. So development, the key messages for the development of costs are by scaling up the production, both main components of the power to gas technology, so electrolyzer and methanation system, show immediate and substance cost reduction behavior related to the scaling effects and technology learning. In early applications, so in 2020 and 2030, the use of surplus electricity from PV or wind does not provide acceptable Sng production costs, so no business case for that at the moment. In Europe, in early applications, power to gas plants will need to run at high full load hours, so higher than 4,000 hours. This is only achievable if you are connected to the grid. So, and the reduction in Sng production costs requires purchasing low-cost electricity, maximizing the plant efficiency, reduction in investment cost, and in case where the plant is connected to a PV or wind park, building the PV or wind park in good location with high full load hours. The development of power to gas technology is subjected to climate and policy measures. So, for example, carbon taxes, the scope of government R&D, subsidies, and market introduction programs, and economic factors. So, from the next steps have to be that we take a look at the policy measures and what is the problem, why power to gas is not introduced in large scale at the moment in Europe. So we have to go from the basic research. At the moment we do basic research, let's say in the power to gas field, to a market penetration. And to reach that field here, we have to cross the valley of death. So we have to reduce the resources of research and start up with the commercializing of power to gas. But how can we bridge here the valley of death to start the commercialization of power to gas? So to commercialize the market, we need a functional market, of course. And that's the current status of power to gas. We have to overcome the valley of death, the functional market for green, where you have to build up a functional market for green gases and monetize added value, because power to gas can be a helpful element for the energy transition. The first policy approach involves measurements to overcome the valley of death, as mentioned. The second approach here considers measures to establish a functional market for green gases. And the third approach considers power to gas more as an energy infrastructure component for grid services, so balancing, transport and storage power to gas is useful for that. The final suggestion consists of details in the current policy, hindering the infrastructure of power to gas, and additional suggestion to help assure a smooth establishment, while all political approaches could meet the same objective here. What we recommend in our roadmap to the European Union is that the European Union should invest money in substantial demonstration projects, so in big demo projects. So one demo project needs around 10 million euros of public funding each. 10 demo projects should be funded with 100 million euro public funding each. So a really big demonstration plan that you can also show that power to gas is able to help the electricity grid and to help the turnaround from fossil fuels to green fuels. The European Union has to introduce policy measures to establish a credibility to potential investors in power to gas, that there will be a serious market for renewables and carbon neutral gases, as well as derived products both in the feedstock and in the energy market. So the feedstock market could be the first market segment with policies. So for example, steel production is one potential market where hydrogen or methane can be used. And if they bring in CO2 penalties, then it will make sense to change from fossil fuels or fossil feedstock to green gases. And to reach the total energy market for gas, the obligatory admixing of renewable gases to the EU gas system seems to be a preferred way forward. We should start that we add 5% of hydrogen or synthetic methane in the grid by 2051, and that based on a guarantee of origin. The same rules, and this is possible with guarantee of origin. And last but not least, we should create incentives for further investment in power to gas with a significant research program. So this was the overview over the power to gas project STORE&GO in Europe. I would like to thank you for your attention. If you need more information about the project, please visit www.storeandgo.info. If you want to learn more about me, you can find me in my profile at LinkedIn or at Grinix.de. It's in German. You'll find information about my company. If you have further questions, which you don't want to ask now, you can also write me an email at that address. Thanks a lot, and now I'm open for your questions.
Okay, no, I want to thank you for your interesting presentation. It's a completely vision or about the state of the art of technology to power to gas, and I think we have a good opportunity in power to gas technology in order to scaling up the use of hydrogen in different sectors and of the economy. And now, as you said, we expect the capex of this type of project to be similar to what happened with the investment cost of photovoltaic energy in the past. Now we will start with the question and answer of the assistant. Okay, we have the first question is, yeah, there is a very specific question. Is CO2 the only source of carbon for biological methanation? What are the bacteria feed it with, and can it be wastewater with organic material used, for example, for this process?
Yes, good question. So first question, for the biological methanation, carbon monoxide is as poison if it's in a bigger concentration in the gas. So for the biological methanation, we should stay at carbon dioxide as a C source, but for the chemical methanation, also carbon monoxide, for example, could be a source to produce methane. So if there's an industrial process, for example, where carbon monoxide and carbon dioxide and hydrogen, for example, is at the end a waste product, you can convert all three medias, hydrogen, carbon monoxide, and carbon dioxide, into methane with a chemical methanation. For the biological methanation, it should be carbon dioxide. But of course, at the end, the second question was if biological mass from a wastewater treatment could be also used, for example. Yeah, the bacteria in that and from that process, from a wastewater treatment plant, could be used to produce methane. Yeah, with CO2 and hydrogen. You have to add hydrogen, and then you can produce in that kind of reactor synthetic methane. So after a wastewater treatment, you have carbon dioxide and methane as a product. And that CO2 can be used with the methane together, added hydrogen to produce more methane out of the end product of the wastewater treatment plant. So yeah, you do not need pure arches, but you can also have a mixture of bacteria.
Yeah.
Here in Solothurn, we used the technology from Electrocare. They have specific archeas and only one sort of, but there are other technology providers which use a mixture of bacteria and arches.
Okay. Other question is related to the size of this kind of plants. What is the size per kilowatt of an H2 plant compared to a gas plant, a conventional plant? There is some different?
Here at the moment, the demo site, the size of the biggest one, this was the plant in Falkenhagen. It was 1 megawatt. So we produced there around 200 cubic meters of hydrogen per hour. And the commercial gas turbines or power plants, they are much bigger. They are in the range of 200, 250 megawatt. So if you want to combine a power to hydrogen plant or power to gas plant with an existing gas power plant, you have to increase the capacity of the actual power to gas plants which are available. But some companies are already thinking about power to gas plants up to 100 megawatts to use the electricity from wind or PV up to 100 megawatts.
Mm-hmm. Other question related with the catalyst. Some person asked what catalyst has been used in the project and what were the operational conditions of the methanation, especially for the case of Switzerland. And yeah, he said, I'm surprised that selectivity to methane is 100%. And
yeah.
you, okay.
At the biological methanation, we used archeas from Electrocare, and they are very selective to convert hydrogen and CO2 into methane and water. And if you have the correct pH value, you give them the perfect nutrients, they are perfectly trimmed, fit to produce nearly 100% of methane. This was not always the case, but after a while we checked some parameters, and then we saw, for example, the stoichiometry of H2 and CO2 was wrong. Then we corrected, and then we reached up to 98, 99, up to 100% of methane. So in one step with the biological methanation. For the chemical methanation, this is not possible within one step. And there we use nickel catalyst in both locations, in Troja in Italy and in Germany, in Falkenhagen. We use nickel catalyst because nickel catalyst is cheap, and also the selectivity to produce methane is very high. So we also thought at the beginning, when we reached nearly 100% of methane, we thought there is something wrong, but at the end we tested it again and again, and we reached it also a day later. But there you really need to have a perfect condition, let's say. It's like we can run a marathon within the best people can run around in 2 hours and 10 minutes, but then the conditions have to be really perfect. Temperature, you have to feed the correct things if you want to be fast, and that's the same for the bacteria in the biological methanation.
Okay, and talking about the the pollution to burn this mix or this blending, adding the process of methanation after generating the green hydrogen implies that the use of that gas will be more pollution than using the hydrogen directly. And methanation implies the gas produced is more polluting than the hydrogen at the time of use. Yeah, you produce hydrogen, green hydrogen, but you burn a mix. And what can you say about the pollution, or the emissions of these things?
Yeah, of course, the emissions of CO2 is, if you produce a synthetic natural gas, is the same as if you burn fossil fuel. But the CO2 should come from an unavoidable source, for example, cement industry, or from a biological source, or from the atmosphere. And then you recycle the CO2. So the CO2, what you put in your process, is also what is coming out. So this is a closed circle if the CO2 is coming from a biological source or from the atmosphere. But there's no CO2 reduction, that there's less CO2 emission if you burn a green methane molecule than a gray. But it depends on the CO2 source. And in future, of course, the CO2 source has to be also a green source like the electricity. Otherwise, it will not make sense.
Yeah, all depend of the source. Yeah, the idea is to try to be neutral in order to not consume or not produce more CO2 at the atmosphere. Yeah. And relate with the point of injection. For example, can the injection of hydrogen into the network be done in any point of the network, or must that happen in a specific place with a specific condition in order to ensure a homogeneous mixture, for example?
Yeah, it depends. There are rules at the moment in Europe where you are not able to inject hydrogen into the grid because there's a limited value. For example, for compressed natural gas cars, also cars driven by synthetic natural gas or by fossil fuel, fossil gas, fossil methane, the tanks are not allowed to see more than 2% of hydrogen. But the grid is allowed to see 5 to 10% of hydrogen. But if then you inject hydrogen in the grid and there's 5 to 10% of hydrogen in the grid, and then you go to the filling station, then you're only allowed to have 2% of hydrogen. So there must be a filter, or you're not allowed to inject so much hydrogen. But this is one reason why you're not able to inject hydrogen everywhere. So if there's a gas fueling station next to your injection point, you're only allowed to see 2% of hydrogen in the mixed gas after the injection point. And but there are several studies done from other projects which say also the tank in the gas car are able to see more hydrogen. It's not a big deal to see more hydrogen in the tank. But some problem is if you inject a high amount of hydrogen, then because of the volumetric energy density of hydrogen, it's 3 times less than methane. So if you inject hydrogen in the grid, you decrease also the energy demand per cubic meter of gas. So you get less energy per cubic meter. So if you want to burn 1 cubic meter of gas, you get less energy, so you have to burn more if you want to have a specific value. And also you maybe do not get the right quality you need for your process. So there are strict limits from the gas grid operators that you're not able to inject more than 10% of hydrogen at the moment to the gas grid, because otherwise you're not in the range of the gas quality of the energy demand you need or the customers would like to see. Mm-hmm. So there are some limitations due to the energy content, and yeah, you have to transport then more gas if there's a high hydrogen content in the gas grid.
Yeah, and related with that, if the hydrogen is to be transported through networks in a similar way to natural gas, what material should be used to build this transport network? What adjust or to certain things to solve or to fix by the when you use or when you want to use the hydrogen in this kind of network?
There are different materials you can use. I think you can use steel or some plastic or some carbon. I don't know the exact word for that. You can use. There are studies where different materials are tested, and you can use or inject 100% of hydrogen in the existing gas infrastructure at the moment, which is used. So I have to take a look what kind of material you are able to use if you want to have 100% of hydrogen. But I know a study, they say you can use the existing infrastructure to inject 100% of hydrogen in the gas grid without some risk on the material.
Mm-hmm. And what are the challenges from a regulatory point of view? For the normative standard codes have to be reformed, or to what is your opinion about the normative standard for them?
Yeah, I think the first step has to be that the gas grid and also especially the hydrogen tanks in the cars are able or are allowed to see more than 2% of hydrogen. Then we can increase the amount of hydrogen in the gas grid, and then also in all end user application, heating, for cooking, and so on. But there are at the moment strict rules, so I think first the rules have to change, but from a technical point of view, most of the applications are able to see and to use more hydrogen than at the moment the rules give you or allowed you. So there's a first of all, the technical rules have to be changed.
Talking about the cost, yeah, I think this is a weak point in the case of hydrogen, because the people, especially the people who work in the gas system or gas distribution companies, they are asking, for example, what the hydrogen compared with the natural gas in order to produce same amount of energy. Yeah, we compare the cost of the millions of BTU and compare with the cost of hydrogen. Yeah, it's a big difference now. But what is your opinion about how to close the gap in this sense, to compare the cost, or there is other thing to consider in order to compare these two prices?
Yeah, I think, of course, the price gap will hopefully be closed up to 2050, but then from my point of view, it's too late to start then changing our energy system to a green and carbon neutral energy system. So the governments have to give incentives and to give the people who would like to invest in the field of power to gas some outlook that in future they will get incentives to for using green gas, green hydrogen, green methane instead of using the fossil fuel. And one way is, of course, the carbon taxes, that if you use fossil fuel, you pay a huge amount of taxes because you emit CO2 from a fossil source. And if you change your source to a green gas, hydrogen or green methane, then you reduce or reuse also the CO2 which is emitted before. So you emit less CO2 and you have to pay less CO2 taxes. I think we have to be with the price level on the same range you are able to be on the same price level with fossil fuel if you add carbon tax on the fossil fuel.
Okay, and in this sense, in case of Germany, what is the German government vision regarding power to gas? There are incentives, they are proposing new things, etc.
At the moment, they are looking more in the field of hydrogen. So they developed a hydrogen roadmap for Germany up until 2050. There has to be a huge investment for hydrogen plants and some demo projects. But at the other side, we also have a gas pipeline from Russia to Germany, where will be new gas produced or bring to Germany. I think that's also necessary to stop the coal power plants and then change from coal to gas. And in the near future, then we have to change the energy supply from fossil gas to green gas. I think the natural gas is a bridge technology to green gas technology later. When we use green gas in a later stage, that we will not need any more fossil gas. But fossil gas is a little bit better than coal, but green gas is even better. But I think this has to be developed step by step. And now the first step is to get to get away from coal to gas, and then from natural gas to a green source like hydrogen or synthetic methane. And the German government is doing at the moment a lot for that. They have the hydrogen roadmap where I think it's 9 billion euros to invest in hydrogen infrastructure and hydrogen demonstration projects at large scale. That you can see how power to gas and hydrogen can be part of the energy system and of the energy turnaround.
Okay, and when you developed the STORE&GO project, what were the main technical challenge and how were they solved? And and continue with the question is, what in your opinion, the most important gaps, apart of the cost, that power to gas technology face?
Yeah, from a technical point of view, I think there must be still some research done to show also the technology in a large scale, so in a megawatt, multi-megawatt scale. But at the demo site, the most technical problems were not the technology itself, so not the electrolyzer, not the methanation. It was more the combination of given technology like cooling unit, gas dryer, that they are integrated in the existing methanation unit. There we had some problems with the integration of the standard units, like drying, cooling unit. But the methanation technology itself works quite well, also the electrolyzer unit. So it was more the combination of the existing infrastructure, of the standard technology with the new technology. It was a big problem at the beginning, but after a while we fixed the problems, and then the plant ran overnight, also 24 hours or even longer, and then we also were able to show that the technology is ready for 24/7 operation.
Mm-hmm. Comparing the three plants or the three demo plants, what is your opinion about the efficiency or the significant difference between these three experiences?
All three, I think, it's difficult to compare because all three have different setups. Because in Troja especially, it's a smaller unit, only 200 kilowatt, and in Falkenhagen you have 1 megawatt, so the size is 5 times bigger, so this is a little bit difficult to compare. But let's say from the efficiency point of view, they are nearly at the same range for the methanation technology. If you take the balance of plant, the liquefaction CO2 capture unit, also in your calculation, then of course Troja has the lowest efficiency because of the direct air capture and the liquefaction unit. But from a power to gas point of view, the methanation technology, all three demo sites are nearly from the efficiency the same. If you have to choose one technology for a specific, or if you want to choose one technology, it depends really on the location of the site boundaries. Are you able, for example, to use the oxygen, or are you able to use the heat? If you have a heat sink next to your plant, then it's maybe better to have a chemical methanation because the waste heat is quite good and at a high temperature at around 200 degrees Celsius. But for biological methanation, you only have the temperature level at 40 to 60 degrees Celsius. So it really depends on the location, what kind of technology you should use or prefer to use for your application.
Talking about the efficiency, you know, we have different ways to produce energy from the hydrogen. In this case, what is the efficiency rate of the complete cycle of hydrogen, electrolysis and generation with hydrogen today compared, for example, to methanization or other ways to produce energy from the hydrogen?
Yeah. So the efficiency of the electrolyzer from electricity to hydrogen is for an alkaline or PEM electrolyzer around 70%, roundabout, plus minus, depending on the technology provider. And if you then convert the hydrogen again to electricity and use a fuel cell, the efficiency is, let's say, around 50%. So the overall cycle, hydrogen, electricity to hydrogen to electricity, the efficiency is around 35%. If you produce methane, then the methanation technology has another decrease in the efficiency because the methanation processes produces heat, and the efficiency is around, let's say, 80%. So you lose again a lot of energy there. But if you are able to store the methane because of the season, then from my point of view, the efficiency is not the critical point here, because you use the power to gas process not as an efficient process to produce methane, but you use the power to gas process as an infrastructure tool to make the overall energy turnaround possible. So you store renewable energy, excess renewable energy for times where no wind or no PV power is available. So if you only take a look at the efficiency, yeah, power to gas will not make sense because batteries or other technologies are better. But if you see at a higher flight level, let's say, over the whole energy transition, then power to gas could be an interesting tool for reaching the goals of CO2 carbon neutrality.
Okay, and going back to the cost, because yeah, there is some question about the Chilean energy cost. You know, in Chile we have a huge potential of produce renewable energy from sun and wind, and we have in the last tender, yeah, some years ago, we have a price under $30 per megawatt for people who offer renewable energy to the grid. And thinking in that, what do you consider is the break-even cost to provide the energy, the renewable energy, in order to do more feasible the possibility to use hydrogen in methanation, for example? What do you think about the cost, or cost in this case, maybe under $20 per megawatt in some cases, and we have a sun a major part of the day, and that is related with the capacity to produce more hydrogen in more hours compared with other countries, for example. What are your opinion about the cost of the top-down cost?
Yeah, if the electricity for PV is produced for 20 or less than 20 or $30 per megawatt hour, then it absolutely makes sense right now to produce hydrogen and sell it to the market, because the production, let's say the efficiency of power to hydrogen is around 70%. So if you have electricity for 3 cents per kilowatt, then the price of the production of hydrogen is around 6 cents per kilowatt of hydrogen, due to the efficiency and the capex cost. So, and with 6 cents per kilowatt of hydrogen, you are, I think, feasible to sell hydrogen over the whole world to the market. Then, of course, there will be transport and logistic costs, but at the bigger scale, could be feasible to produce hydrogen with that low electricity price to be competitive to the world market.
Mm-hmm. And talking about the sense to make a mix with hydrogen and methane or natural gas, what percentage of CO2 emission are reduced in the combustion when you use a mixture or a blending with natural gas? I think it's not directly, but can you explain about that?
Yeah, let's say because the energy density of methane is 3 times higher than hydrogen. So if you want the same amount of energy, you need 3 times more hydrogen than methane. So yeah, to save, you will save a huge amount of CO2 if you convert everything from methane to hydrogen. With a mixture, I don't have an exact graph or percentage how much CO2 you can avoid, let's say, if you add 20% of hydrogen there.
Mm-hmm. Talking about the emission in the end point, or when you use the hydrogen or the mix, etc. One question here is, how developed is the technology of heating using hydrogen? For example, for heating homes, thinking in this kind of application. What is your opinion?
Yeah, there are some market players which provide already complete energy solutions for houses or for big houses, that you use solar power from the roof or from the building and convert it into hydrogen if you do not use the electricity for cooking or for TV and so on. If you have surplus energy, you can convert it and store it first in a battery, and if the battery is full, you can convert the electricity into hydrogen and store it in tanks. And then after a while, you can convert again the hydrogen with a fuel cell, for example, into electricity and heat. So you have in a house, if you have a high heating demand, that kind of solutions are very interesting, because the conversion of the hydrogen into electricity and heat, you have an efficiency of nearly 90–95%, because you can use the waste heat from the fuel cell. There are a few suppliers in Europe and also in other countries, of course, they build complete energy solutions on the renewable energy, storing the excess energy in form of hydrogen. So heating with hydrogen is possible if you have at the same time, let's say, an electricity demand. Then you can use fuel cells, and they are quite well developed for house applications.
Yeah, we understood you're producing green methane or green gas, and some question is related with the new e-fuels, and is there a development to produce ethane, not methane, ethane from H2 to replace, for example, the feedstock to the I don't know, the different industry, chemical industry, or using it in a cars, etc.
Yes, there are several companies which are looking at different end products as hydrogen and methane, but they are more looking in the field of methanol or gasoline products. So not maybe ethane, but methanol and some synthetic kerosene and synthetic gasoline and diesel. But I think methanol can be easily used as a feedstock for the chemical process. I think ethane can be also produced, but it's a little bit difficult, more difficult than producing methane. You will need another catalyst, but I don't know if there's a project at the moment in Europe that produces ethane instead of methane or methanol. Most of the Power-to-X projects are now in the field of methanol.
Yeah, there is here more question, but yeah, with the time we have to go closing. But I want to ask the last question. How do you see? Yeah, you have a company now, and how do you see the market for this type of solution, the green gas production, sector coupling, etc. How are and then how are the German gas operator are dealing with it?
Yeah, there are one German gas operator. They now invest due to the government investment also, they invest a lot now in the hydrogen infrastructure to make research in that field, that they are able to phase out the fossil fuel and change to hydrogen. So at the moment, most people or most industries, and also the gas industry, is at the moment looking more in the field of hydrogen instead of methane, because they say the phase of methane will run out and we will change directly to hydrogen. So most companies are now dealing more and more in the field of hydrogen and looking for places where hydrogen can be produced very cheap. And that's not in Europe, maybe in Italy and in Spain in the south, but I think more in Morocco, in Chile, and maybe in South Arabica. But yeah, they always, all companies are looking now for incentives from the government, because it's not economical and feasible at the moment to build such a plant. But if they get money from the state, they are at the moment ready to run, let's say. They have all the plans on the table and are only waiting for some incentives.
Perfect. Okay, thank you, Jan. The time is over, and I would like to thank you very much. It's a very interesting presentation. I think we know more about the power to gas now, and I think thank you very much. And if you, if the people has some question, we will send directly to you in order to answer. Yeah, I know we have more questions, but the time is limited. Okay, thank you very much, Jachin. Be well, be careful. And voy a cambiar el idioma. Bueno, solo para despedirme, muchas gracias a todos por la presencia. Todavía tenemos muchas personas conectadas. Creo que esta es una oportunidad también para Chile en relación a poder utilizar el hidrógeno en estas redes que ya están establecidas. O sea, son redes creadas donde ya hay una gran cantidad de infraestructura creada de tal manera que puede llegar a distintas partes sin tener que hacer una reforma mayor. Obviamente tiene que ser adaptada, tiene que ser establecido también la forma de operar, los estándares, la normativa, la regulación, pero creemos que esta es una gran oportunidad para hacer un escalamiento del hidrógeno a un gran nivel. Así que solo dejarlos invitados para la próxima charla, que va a ser de calderas con hidrógeno, súper interesante, especialmente en el área industrial. Así que ya estarán recibiendo nuestra invitación. Muchas gracias a todos y nos vemos en 2 semanas más. Que estén muy bien. Thank you, Jachin. Bye bye.